So these two videos that you're going to be watching are connected with lesson 6.6, and in this lesson we're going to be switching gears a little bit. So far this chapter we've been talking specifically about radical functions, but in this section we are going to go back and start talking about some ideas that are related to function notation. You might be wondering why these topics are showing up together in the same chapter. And the basic reason is that now that you're familiar with radical functions and polynomial functions and quadratic functions and all the other types of functions we've talked about so far this year, there's a little bit more that you can do with the ideas that we're talking about in this section just because you've been exposed to various types of functions. So the first thing we're going to be talking about are just some basic function operations that you can do using function notation. And aside from the notation, this shouldn't be anything that looks too crazy to you all. We're just going to be looking at the four basic operations: addition, subtraction, multiplication, and division, but representing those four operations using function notation. So first of all, let's review exactly what function notation is, because it's been a little while since we've used it. Remember that function notation names your function with a letter, typically f, and then we're going to define our function as usually f of x, and then we're going to say that f of x is equal to whatever our function is. So let's just do something simple and call it x squared. So that means that f of x represents exactly the same thing as y does. F of x is your output, x is still your input, so we could rewrite this as y equals x squared if we wanted to. That's slightly more familiar to us. But function notation is helpful, or useful, I guess I should say, because you can choose various inputs and you can specify exactly what input that you want to evaluate your function at. So, for instance, if we want to evaluate f of 2, that simply means that wherever x shows up in our function, we're going to plug 2 in for that. And so, of course, f of 2 in this case is 4. So, using function notation, we can then represent our various function operations. We can add two functions together, we can subtract them, we can multiply them, or divide them, which is exactly what I've got going on here on this slide. So we have two functions that we're dealing with. One is f of x, and the other is g of x. And we are performing various operations on them. Now, this first notation simply says that we are adding our two functions together. So when you see this notation where f plus g is in parentheses and there's an x after that, it doesn't mean that you're multiplying by x. What this means is that you're taking the function f of x and you're adding on the function g of x. If we are subtracting our functions, that simply means that we're taking f of x and subtracting g of x. If we are multiplying them, you can probably figure out this just means f of x times g of x. And finally, if we're dividing them, that's just f of x divided by g of x. So nothing too complicated there. Let's do a couple of examples. Okay, so I've defined these two functions. F of x is going to be 2x squared plus 8, and g of x is equal to x minus 3. So let's say we want to see what the function f plus g of x would be. So remember, that just means that we are adding f and g together. So that's going to be 2x squared plus 8 plus x minus 3. And then, of course, you probably want to simplify this a little bit, so we combine like terms, and our combined function is 2x squared plus x plus 5. If we want to evaluate f minus g of x, of course, you just subtract your two functions, so we've got 2x squared plus 8 minus x minus 3. And just like we did a moment ago, you're going to combine like terms. So we'll end up with 2x squared minus x plus 11. And then we can do the exact same thing if we are multiplying or dividing our functions. So if we want to multiply f and g together, that's that's just going to be 2x squared plus 8 times x minus 3. And then since we're multiplying two binomials together, we would of course just FOIL that. So we'll get 2x cubed minus 6x squared plus 8x minus 24. And then finally, if we want to divide our two functions, f over g, then that's just 2x squared plus 8 over x minus 3. So that all is pretty straightforward. What you do want to think of, though, is you want to think about your domain here. And that holds true for all of these combined functions that we just created. Remember that domain describes the set of x values that your function can take on. Personally, I think an easy way to think of this is, does your function have any values of x that aren't possible? And if so, they would be excluded from your domain, and then your domain is just what's left over. So let's go through these one by one quickly. Our first function that we looked at ended up being 2x squared plus x plus 5, and this is when we added our functions together. So I can look at my function, and there isn't any value of x that I can't square, and there certainly isn't any value of x that I can't just add on. So that means that our domain here is all real numbers, because x can take on any value we want. Same holds true for our second function where we are subtracting the two. There isn't any value of x that we would be excluded from plugging into this combined function. So again, our domain is all real numbers. And remember that if your domain is all real numbers, you can use that fancy script R to describe that. You can say it goes from negative infinity to positive infinity if you want to use interval notation. Okay, last two possibilities. Our third function, when we multiplied our two functions together, was 2x cubed minus 6x squared plus 8x minus 24. Just like our first two examples, our domain here is going to be all real numbers because there's no value of x that we can't plug in there. We're finally going to get to something interesting here in our last example where we were dividing. Since we have a fraction, of course, you can't have a 0 in your denominator, so we need to figure out what value of x would create a denominator of 0. And if our denominator is x minus 3, we can't allow x to be positive 3, because of course 3 minus 3 would give us that 0. So x, in this case, since it can't be 3, our domain is all real numbers except for positive 3. So if you wanted to write that in interval notation, you could write from negative infinity up to positive 3. And then, didn't give myself enough room, just a second. Here we go, I'll write it over here. So we can go from negative infinity up to positive 3, but we don't include 3, because 3 cannot be in our domain, so we use parentheses. And then we use that big U for the union, and then give the rest of our domain. Our domain also includes all the real numbers between 3 and positive infinity.